right, part two. Part two is not spectacularly difficult. Basically, all part two is saying is that when you've got two fields, two things producing fields, the field that something sees is the sum of the fields from each one. Now, this is a little bit conceptually difficult because what will happen is you'll have, let's say an object here producing a field, doing whatever it wants to do, right? And then an object over here producing a field, doing whatever it wants to do. And then what you have to do is at each point in space, right, you have these guys producing their fields, which don't have to be, well, I guess they have some sort of relationships that make them consistent, which I think I've messed up on. These guys have to go this way. So they have these relationships that sort of make them consistent, so that you have these fields doing all their things. Well, when you have these two different things making fields, right, the field at each point is just the sum of those fields. So, I screwed that up again. All right, so that means I've got green and red, and purple. That means at this point, right, we have the green field going this way, right? This is the direction of the green field. And the red field going this way. The purple field, or the sum of those two fields, this plus this, is equal to something like that, right? And you can go to any other spot. Now, these lines just sort of indicate strength. The farther away the lines are, the weaker the field, and the direction is given by the arrows. So this sort of tells you stuff, but it is meant to be read sort of qualitatively. So if we have a green field going this way, a red field going down that way, the purple field has to come in somewhere in that direction. So at each point in space, this field is being added or subtracted vectorially, right? Or added vectorially, technically. So it's always being added vectorially. So all that vector stuff you did in Physics 1 still shows up here because the field has to do with a force, and each source creates a field. They add together to make a new field, or to make a total field, which is what your object reacts to, right? Just like in Newton's second law, you use the net force, the sum of all of the forces. Well, you get a force from the effect from this guy and a force from the effect from this guy. Those are in that field, which produces a net electric field that you respond to. So it doesn't matter if you can do it either way. You can either find the forces due to each field and add them, or you can find the fields from each source, add them, and then find the force from that. It's exactly the same thing. That's called superposition. That's the principle of superposition. It underlies all of fieldy stuff, right? Stuff that has to do with fields. And for you, that's going to be, or I guess, linear fields. Only linear fields can superpose like that. But everything that you're going to do in this class, for you, it's electricity and magnetism. It's also true for velocity fields in water, for example, in fluids, so that all of these techniques will work in fluid flow and things like that. But we just use them in terms of electricity and magnetism because we only have so much time, right? I mean, if you want to get into fluid flow, plenty of courses on fluid flow. You'll love them, obviously, because you love fluids. But that's just not what we do in this particular course. So, well, I was using green, so I should probably keep using green. What I just said is when you have multiple fields, you have it in the same space, add vectorially at every point in space, at each point in space. Should be each point or at every. I think probably each is the better choice, right? Okay, so that's the basic idea behind those. And so, you, like I said, you can do that one of two ways. You can say, okay, the force at any point x is equal to the charge on the object, just like we did in the last video, in part 1, times the sum, little summing thing there, of each of those fields produced by different sources, or the force at a point x, I should write x here, is equal to the sum of all of those forces, so which is equal to the sum of Q times E for each one of those forces x. Okay, where this Q is the force of the thing that you put here, right? This has the charge Q, remember. So these guys might have charges, but that doesn't count. It's only the object that you put there in the field that counts for this, at least. For anything linear, and electricity, magnetism, they're linear. That makes life nice and easy, comparatively. You might not think so for the purposes of this class, but you wouldn't want me to give you a nonlinear field. All right, so we won't do anything like that. But you know, for this class, it's comparatively easy. You just have to add things vectorially. So we'll do a little bit of that in the example, and so we'll remind you of things like the Pythagorean theorem and other fun things that I know you wish you could forget. And you can't forget them, not till the end of the class. All right. I don't know what you're going to do after the end of the class. You can forget them after the class, but till the end of the class, probably you don't get to forget the Pythagorean theorem. All right? Bye now.